We'll wait for a couple of minutes more, then we can start, okay?
Is my screen visible?
Yes, sir.
Yes, bro.
Okay, so I'll be starting with the third week, which we have been continuing. Last week we saw, I guess, sorting, searching, and everything, right? If I'm not wrong. So I'll continue where we stopped. I guess that was around searching. So we saw binary search, linear search, and then using STL for that. Then now I'll be taking graphs and dynamic programming for you guys. And for graphs, I'll be going through BFS and DFS. I think those are the only ones required. And in DFS, there are two other ones called as limited depth search and iterative depth search. So these two, I guess, will be main for competitive programming when you have to reduce the time complexity using DFS. And for BFS, there's no other optimization technique for BFS where you can reduce the time complexity. So this is what I'll be taking ahead, and I'll be giving you a basic intro for graphs as well. So let's start with graphs. What is graph? It's a data structure just like trees. What is trees? We'll be learning again tomorrow's session, more about trees. I'll just be taking you a graph. And in graphs, there are instead of nodes, there's something called as vertices, and the line connecting two vertices are called as edges. And each edge, and there are, if the two vertices are said to be adjacent, if they're connected by a single edge. So let's understand the terminology before we go through like BFS, DFS, or something like that. So basically, vertices adjacent to a given vertex are called neighbors, and the path is a sequence of edges. And a graph is said to be connected if there's at least one path. And a non-connected graph consists of several connected components. And I'll give you some ideas. So basically, this is a path. If you start from here, this is a path of length 4, 1, 2, 3, 4. And vertex is nothing but any node like in a tree, and edge is nothing but connecting two vertices. A cycle is nothing but a closed connection between the number of vertices. And vertex of degree is nothing but the number of vertices connected to this. So here in this case, 1, 2, 3. So 3 connected components are there. That's what it means. This is for undirected graph. And for directed graph, I'll be telling you what is out degree, in degree later on. Next comes reachability. So vertex is reachable from B if path exists from A to B, and connected. A graph is connected if every vertex is reachable from any other this thing. So now you can say this graph is connected because this vertex is reachable from this, and this. So this is a connected graph. But if you see this vertex, this is not connected because this vertex is not reachable to this. So that graph is called a non-connected graph. As simple as that. And let's go towards the two types of graph, which I told I'll be explaining you. So first is undirected graph. It's nothing but as simple as it's just connected and there's no direction given to it. So we have no idea if A is going to C or C is going to A. It's as simple as that. And degree of a vertex for A is nothing but the number of edges connecting to it. Basically, number of lines going to it. So A degree over here is going to be 2. As simple as that. But whereas directed graph over here, it actually shows you where it goes. Like suppose if there's two lines here, that means A is going to B and B is going to A as well. But if there's only one pointing to it, one arrow pointing, that means A is going to B. So like here, if you can see, C is going to D, but D does not go to C. But in undirected, it means both are going towards each other. So as simple as that. And in degree, while I was discussing here, you could see in degree and out degree. So in degree is nothing but the number of inbound edges. So for A, if you see in degree is nothing but B is going inside A. That is nothing but the in degree. And out degree is something which is going out of A. That is A going to B. That is nothing but as called as out degree vertex. So for A, in degree is nothing but 1, out degree is also 1. For D, in degree is 1, out degree is 0 because there's nothing connecting to something else from D. But there's something taking into D. So C is connecting to D. That is what in degree and out degree basically means. Now, basic graph terminology we'll be discussing more. Walk is nothing but a sequence of X to Y where basically any loop or anything you call it as a walk. Like you can take it returns back to something like that. That is what is called a walk. And path is where basically no vertex get repeated. So you can take a walk, and path is nothing but uniqueness. Basically, as you can see, A, B, C, D, D, B, A, C. This is getting repeated, so this cannot be called a walk. Path should be connected as well. You can't take A, B, C, D because A, B, you can take it. It's not that issue. So you can take any one of them, but it should not be repeated. So A, B, C, D, that's also path. A, B, D is also path, but A, B, D, C is also path. But A, B, D, C, B is not a path. And cycle is nothing but all the vertices are interconnected to each other. Basically, it forms a loop, indirectly saying. So A, B, D, C, A is nothing but a cycle. You can take A, B, C, A. That's also a cycle. As simple as that. And this we already discussed, graph definitions, simple path and cycle and a simple cycle. Let's go to graph. Now, how can a graph be represented? So this is something important because in your competitive programming, you will be given graphs. I guess I told you guys to solve LeetCode, right? So in LeetCode, you would have come across at least one question where a graph would be given, and you would have to find out something like the minimum depth, the maximum depth given with a subarray K or anything like that. So how do you convert this graph given into something which you want to represent and find the output? So there are 3 possible ways. One would be array, one would be list, and third would be other data structures which you would like to use, that is a linked list, anything like that, but depends on the complexity of the problem. Now, if it was just to find the depth of the graph, you can just take an array. But if you want to find the minimum leaf nodes or something like that, you can store it in a list, and then leaf node is nothing but the edge of the graph. So that's when you take it as a linked list and just find a pointer where the last edge basically doesn't connect to anything else. So that is nothing but your leaf node. So based on the question, how they have asked, you can decide which data structure you want to use and try to find out your maximum output or solution. And other way you can basic representing of graphs can be done by adjacency matrix, list, or multilist. So this is the most basic if you're going towards AI or anything for path planning or robot something, because I'm in AI robotics. So this is something very important, adjacency matrix and list, because if you want to make a path planning for a robot, or if you want to find a path, any given path, not robot, not this thing, even in competitive programming, if they say find a path of a graph, they will give you a format of adjacency matrix or list itself. They won't give you the graph. They just give you this, and based on this, you have to find the path. As simple as that. Let's go towards what's an adjacency matrix. Adjacency matrix is simple as this. If the let G be V comma I, where V is the vertices, E is the edge. So it's as simple as this. If there's an edge where it's connecting, it's 1, or if there's no connection between the two vertices, it's 0. As simple as that. So if you take this example, I don't know if this is visible or not. Tell me if it's not visible for you guys. So if you see 1 and 0, 1 is connected to 0. Let's take this as 0, 1, 2, 3. So in 0, if you see 0 gets, if you see for 0, 0 is connected to 1, so it's 1, and it's not connected to itself. If you want to make this connected to itself, you should loop this. So when you loop it, that means it's connected to itself. And then when you check 0 to 2, is it connected? Yes, there is a line. So you keep it as 1. And is 0 connected to 3? Yes, it is connected. That's how you keep doing this, and you finally find it. So these are the 3 examples I've given. When I'll share the PPT, and when you're not able to understand any one of these examples, you can always contact. This is how the undirected graph adjacent, undirected and directed. So if you see here 0 and 1, in 0, it is connected to 1. Why? Because this arrow is pointing towards 1. That's why you put it as 1. Is 0 connected to 2? No, you can see no line. 1, is 1 connected to 0? Yes, because of this line is connected to 0 in directed graph, because 1 is pointing towards 0. Is 1 connected to 2? Yes, it is connected. And 2 is connected to nothing, because you see there's only one input, there's no out degree, so it's not connected at all. Now let's move towards adjacency list. So if you are solving questions and if they give you in type of list, so this is how you'll be doing it. Instead of matrix, simple. Instead of matrix, which is stored in a matrix, you'll be getting it in a list. Like I told you, right? You can use linked list to find the leaf node. So I guess leaf node would be the perfect example of why do you need list. So if you use a list and see here, as you can see, this is pointing to 0. So that's what it means. So this you can find the leaf nodes. So linked list is the best possible way to find anything edge cases of a graph. So if they give you a graph and ask you to like edge cases, something which is outside, a linked node would be easiest way. Simple, take A and point it towards whichever is connected. As you can see, A is connected to B. So it's getting pointed towards B. Is A connected to this thing? Nothing else? No. B is connected to A. So it's pointing towards A. Now C. Where is C getting connected? D. And C is getting connected to B as well. That's why it's getting 2. And if you check B is getting connected, no. That means this is your leaf node. If you through your linked list, you can get leaf nodes or any edge cases. And D in this is not getting connected to anything. That is why it is 0 or null. So you can count this as one of your leaf nodes or your empty nodes or anything like that based on your questions. So here are basically more examples based on this, like how I've taken previous examples. So 0 is connected to 1, 1 is connected to 2, 2 is connected to 3. That's how it is. And 3 becomes your indirectly your endpoint or a null point. And if you check 1, 1 is connected to 0, 0 is connected to 2, 2 is connected to 3. You can go anywhere. You can get 1 to 2, 2 to 3 as well, but you have to get the max possible connections. That's why you prefer going like this. And 2 is connected to, you can even go like this. The minimum you have to go. So 2 is connected to 0, 0 is connected to 1, 1 is connected to 3. That's how your adjacency list will be formed. I am going fast in this because you just need to know what a list or a matrix is, because in the questions which they give you in competitive coding or programming is they'll just give you a list. So more this thing comes in how you apply your search algorithms in your graph. So just know what it is. If they give you a list, you should actually identify or get to know how the graph is going to look. Because if you don't know how the graph looks, then you're not able to solve the question. So when I give you this list, I need this graph as an output, as simple as that. So you just need to know the basics of list. This is not like this thing where I sit and explain how to form lists, just a basic of how list actually works. So you get to know what a list is. And then what I told was multi-list as well. Multi-list is nothing but a mix of both a list and a matrix. That's it. That's the only thing. And this is how your basic undirected graph adjacency list and matrix looks like. for another example. And this is how your directed graph looks like. The only difference here is you can see here, right? It can't loop itself because there's no direction given to it. So if there are loops like this, then 6 is connected to itself. So you have 6 connected to 6. So be careful of the directions. That's what this thing is. It can even give you a clue whether the graph is directed or undirected based on that. After this comes the main this thing where you actually use your graph algorithms, where BFS, DFS, all of them go on weights. BFS, DFS all go on weights for finding the thing. Weighted graph. Basically, here you can find your shortest path, which is called A-star's algorithm, and your A star search. You can look up on it, heuristics and cost values. So all of these comes from a weighted graph. So from here you can find out your shortest path to wherever you want. So if this thing was going from path C, so I have two options. Path C would be A, D, and C, and A, B, D, C. So I have these two options. If you have a non-weighted graph, you won't know what or where to proceed. So simple, if you find weighted graph, just calculate the total weight. If I go to A to B, it's 8. B to D, it's 2. So 10. D to C is 10. 10 plus 10, 20. But if you go from A to D, it's 3. D to C is 10. It's nothing but 13. So the shortest path here would be 13. So this is very important in upcoming this thing, because there are questions where they ask you the shortest length or something like that. That's when you use your shortest path algorithm, where basically you just calculate the weights. And if one is lesser than the other, store that. If A of I lesser than A of J, whatever your path, this thing is, store that in your minimum. That is how your weighted graph goes. And in adjacency matrix, where we used to, if what I told, right, if both of them get connected, if one is connected to 2, it's nothing but 1 or 0 we were represented, as simple as that. But when you have weight, you represent its weight and its adjacency matrix or cost matrix. I'll prefer using cost matrix from now on when there's weights. So you get to know the difference between them. So if you see the previous example, A to B are connected, yes. And what is the cost of it? It's nothing but 8. A to C is connected, no, it's 0. And A to D is connected, yes, the cost of D is 3. Moving on is going to be the same thing. B to A, since it's undirected, you have both of them are interconnected. So B to A is also 8, and it keeps going on like this. If you have any doubts in between, you can stop me and ask if you didn't understand, because I'm going a little bit fast in this, because this is just basic knowledge for CP. You don't need to really know what happens in this. You just need to know if they give you a cost matrix, what does it mean? If it's 1, 0, 0, it means it basically has no weights. And when you don't have any weights, how you proceed? You go through another search, heuristics or something like that, whatever they give you. And if it does have weights, you go towards BFS, DFS, where it goes on your weight searching. Next, we'll go through the main thing, the graph traversal techniques, which I was talking about. Well, the first one I'll be going through is depth first search, and the second would be breadth first search. And after this, there are more graph traversal techniques, which I won't be teaching now because you need greedy optimization. You need to learn greedy optimization, which we'll be teaching later. After that, there's something called as greedy best first search. So what does that do is completely different from these two. What greedy best first search is, it just cares about the cost. It doesn't care about the shortest path. If your cost is the shortest, it just goes towards the cost. It doesn't care about the what path you take or anything like that. That's the only difference. It's optimized, slightly optimized than these two. Not that much optimized, but yes, sometimes it passes your test cases. So do go towards greedy best first. We'll be explaining that to you in your next session as well. So let's start with DFS. DFS is nothing but depth first search, where basic ideology of DFS is we visit a vertex V and from another vertex U, start vertex U, and then we recursively visit a neighbor of V that has not been visited before until all neighbors of V have been visited. And then we backtrack and return to U. Now, what does that mean? I'll take this example and show you. So this is your graph. Simple. This is your start vertex U. Consider it as S now. Start state and go state. So what happens is it visits its first neighbor A. When it visits, it's nothing but A. Now what it does is it tracks and visits all the neighbors of A itself. It doesn't backtrack. So now what we do is visit all the neighbors of A. It has visited A, then the next neighbor is D, then the next neighbor is G. Okay, this is what it has reached. Now what you do, backtrack, go back again and visit next. Backtracking will give you backtrack from G is E to B, and P to this thing. Again backtrack, G to F, F to C, and back to S. That's what you mean by backtracking. This is your basic DFS, and this is the algorithm. If you don't understand any part of algorithm or something, you can check it once and let me know. And next would be why analysis of DFS, like why DFS is not as popular as I told you, right? There are two more methods of DFS which we use now to reduce time complexity. So it's simple as this. Exponential time. The time complexity of this, as you mentioned, exponent time complexity. You are not supposed to have any time complexity which is exponential. And here we have an exponential time of b power d, where b is nothing but the branching factor, that is number of branches, and d is nothing but the depth. So you will realize, like, I hope you guys know, right, how much of a problem this is if you are considering time complexity as exponential time. And even space complexity, the space complexity is b into d, which is okay, pretty good. The only issue of why DFS won't be used is this graph is small. It has only around like 7-8 elements. How much? Now, what if I have 200 elements? So imagine, and 200 elements, the depth is like around 200 and the branching factor is around 5. So this will give you a time complexity of 5 per 200, which is an issue. Kind of screws up your whole code and you can't do anything because of it. So that is why we have two other options of using DFS or optimizations of DFS called as depth limited search and depth first search. Depth limited is kind of luck based. Not luck based, because of depth limited, you have to put another this thing. It works as it's said, as simple as this. You put a depth limit. Suppose the graph here is depth is like 1, 2, 3. Now, if my goal is to find B, okay, what DFS does is as simple as this. It goes 1, 2, 3, 4, 5. Sort of 5 searches it gets B. Now, if I limit my depth to this, that's it. My depth is 1. I don't go more than 1. What does it do? It goes here A, it finds nothing, backtracks, comes towards B. So it finds this in second. So how faster is this? So for this, you have to understand what code is given, what question is given, and what logic to apply. So if you do that, and if you can accurately calculate where the depth would be, but not calculate where it actually is, then you would go towards this search, because it becomes so much more faster. It just found in second step. So look how much the time complexity has changed from searching from 5 to 2. It has reduced by less than half. So this is but only issue is you have to find out what depth it is. So again, the modification of this comes towards your depth first iterative deepening search. So what it does is you take a cutoff depth, like here you have taken 1. But what if it's not found in 1? What if I wanted to actually find E but not B, and I assume my depth as 1? What do? They keep another loop where your depth keeps increasing. So this is 1, C equals to C plus 1, which I've said here. So if you don't find it as 1, I check here 1, 2, 3. You don't find it. So go towards the second depth. Or here you check 1, 2, 3, 4. You find it. You keep finding. What happens is one less searching. This third depth gets eliminated. So again, it shortens the time complexity, but it will be a little bit more slower than the depth limited search. But obviously, everything has its advantage, disadvantage. So here, you don't need to actually know the depth of the graph. It's as simple as that. So that is why you use your depth DFID, depth first iterative deepening search. If you have no idea where your depth is, if you have an inkling, like, you can use the recursive one, which I showed you, divide and conquer, right? So what you do is, if you have 5 depths, okay, divide it into half. So if you have 5, make it as first one will be 2, other one will be 3. So if first one is 2, start from 0 from there and end it till 2. And second one is 2 to 5. So start from 2 depth and end it till 5. So this is how you can go with recursion with depth first iterative search as well. So you have no idea what the depth is, but you want to attend the problem or the solution of this question in a faster way, use DFID. And if you have an idea where the depth is, like a proper pinpoint of where you can find your depth, use depth limited search. Moving on to the next would be the most famous one, I guess, if you use in CP, would be BFS. Though its time complexity is very long, you use BFS obviously for shorter graphs, and BFS is more better to use than DFS, because what it does is it is nothing but a level order search. Simple. If you're given a node V, it visits itself first, and then it visits every node adjacent to V before any other nodes. So as simple as this. You have this graph. So this is V. First it visits itself. Then it visits all its neighbors, that is A, B, and C. So first it visits A, then its second neighbor B, then its third neighbor C. After that, you go to the first neighbor which you found A. Then it visits all the neighbors of A, which is in this case D, nothing else. Then you go towards the second neighbor which it had visited, B. It visits its neighbors as well. That is nothing but E. After that, it goes to its next neighbor which it had seen, C. And finally, it visits C's neighbor, which is F. and then backtracks again, goes towards D, which is what we have visited after A. Finally, from D, you go to G. So this is how BFS works, and why BFS is more used than DFS. As simple as this. If you have no idea how the graph looks and if you have no idea how it is working, I just give you a random input of 200 inputs of different types of graph, and I want you to find the end state or wherever I want you to search. In that case, DFS would not be DSS, or what are those two, depth limited search, DFID would not be plausible because you have no idea what graph, what type is coming. So BFS would be the safest option, I would say. Obviously, the time complexity is more than DFS. It's not that it's less. Space complexity, I mean, time complexity are the same because branching factor to the power of depth. That's how it searches. The only issue would be you have no idea what is going on. So when you have no idea what is going on, the safest would be BFS. So here I said, as I said, it is time complexity is in BPRD, but the only issue is BPRD is its space complexity as well. Why? Because it has to keep all the nodes in its memory. So what DFS did was it went to S, to A, to D, to G. And after that, it removes just A and D. It's not necessary and it backtracks. But what BFS has to do is it has to keep A in memory, B in memory, C in memory. Then after that, it should come to A to D. So it has to remember every single node. That's why its space complexity is higher. So here time requirement is still the same, but space is the biggest problem here because time complexity, they'll give higher, like many times they give until like log n or anything like that, and log n or n cube, somewhere it goes till n cube as well. But space, they don't give a lot. Space is something which they really need you to like restrict using, because if your space is more, indirectly you can brute force. So if you guys know what is brute force, right? Basically, if you have given 1 to n elements in array and you have to find divisor of any number, all you do is just iterate through all the elements and then find all the numbers. That's nothing but your brute force. So BFS is nothing but brute force of graph indirectly, because all it does is literally checks every single node and then finds out. So there's nothing but brute force, and brute force main issue is time and space. So in CP, your space is less because they don't want you to use brute force. I guess only a problem of code force will have brute force based on rating wise, I'm telling you. So I'll just tell you how rating starts. So A has like around 1000 ratings. So it keeps increasing by 500. So only one problem out of all the problems you can do brute force. And if you're really lucky, first two problems. After that, you are not able to use brute force at all. You have to use a search and optimize search. Now, how do we optimize this? I already told you when to use what. How do you optimize searches? So as simple as this. There are two optimization techniques for any code you want to run. One is dynamic programming and one is greedy algorithms. I will be, for this class, I'll be teaching greedy algorithm with an dynamic programming with an example for LCS. And after I give you the answer, like after I tell how LCS is longest common subsequence, I want you guys to go to LeetCode and try all the possible longest common subsequence problems in LeetCode. They're pretty good ones. They have like LCS with a variable k where you stop it at k. So pretty good ones, and try to optimize it to your best possible time complexity you can get. So there are time complexity, and it even shows you what percentage of ranking you have done faster than the people, your time. So look into that and try to give it in your try to do your best possible time complexity using dynamic programming. So what is DP? It is nothing but when I explained divide and conquer, I told you about recursion. The only issue of recursion is nothing but time. Although it reduces your space because of this thing, but the only issue is your time. Your space is gone, but what about your time? So that's when DP comes in. What it all obviously does is it's simple. It is an optimization technique where you apply to it where there can be many solutions. And each solution has a value and wish to find a solution with the optimal value. It is a way of how do you reduce recursion in DP is simple. You have a sub problem. You have divided a problem. Like this is your tree and you divide this into 1, 2, 3. Okay, this is your problem. In divide and conquer, how we divide it. Now you get another problem here. You divide this again, 1, 2, 3. And you get another problem here. You divide this again. Okay, this is how your divide and conquer works, right? Keep dividing. So the thing is, what if this subproblem and this subproblem are the same? You waste your time because you divide this, conquer it, and you come back here and divide it and conquer it again. Why? Because you're not storing your values. You're not storing any of your things. Whatever you found this value, right? If it was sorting, you found like if this is 3, 4, 3, 1, So you got to know 1 should come before 3. Now again 3 comma 1 comes here again. Again you should do the same thing again. I'm just giving you an example, but imagine if the problem is big. So as simple as this, store the values. If this is occurred before, use the same thing. You cut this completely. As simple as that. This is how it works. That's what DP does. There are two types where you can do. One is memorization and one is tabulation. And I'll be discussing about both in the next slide. Others I already told you difference, and elements I've already told you as well. Yeah. So now let's go with this example, which is nothing but Fibonacci series. I'm pretty sure everyone knows Fibonacci series and no one has a doubt of how this algorithm comes. So when you see here, when you actually do, this is nothing but a recursive algorithm, right? Because it's returning fib n minus 2 and n minus 1. Okay, now if I give the start as 5, this is my input, n is 5. What does it do? It goes towards first Fibonacci of n. Yes, it starts with fib 5. Then what does it do? N minus 2 is nothing but 3 and n minus 1 is 4. Okay, and then it comes to this one. Obviously, it has to solve, right? Divide. So once you divide 3, it goes to this. So division of this, again, it comes to n. Then this n minus 2, it becomes n minus 1. And then you get fib 0, fib 1. I go to the other side, fib 4, get it to fib 1 and fib 2, and then fib of 0 and fib of 1. The problem here is, if you see this, the time complexity becomes exponential, right? Because of the amount of searches. Because I already told you, when you do BFS, DFS, right? When the graph, what is it? B par D. That is what your time complexity is of this question, this case. So how do you reduce it? Simple. Memorization technique is nothing but store every single value which you have got in a table. Okay. Store this in a table, column, whatever you guys call it you want to. Simple. Store the value of fib 0. This is a top-down approach. Why? Because you're going from fib 5 to fib 3 to fib 4. You're breaking it down. So when you have a top-down approach, your table filling becomes a bottom-up approach. How do you do it? You take fib 0 first, you fill the value. What is Fibonacci of 0? It is 0. Fibonacci of 1, it is 1. Then you go up again. Fibonacci of 2, it is nothing but 1. You keep storing these values. Now, what is the use, would you say? Now, I've stored all these values that if you know divide and conquer, it divides this, solves this, solves this, solves this, solves this, then goes back to fib of 4. And then solves this, solves this, solves this. So you have solved all of this. So you know the value of literally every single element. Now, when you store this, it's simple. Fib of 4, is it written? Do we have it? If you start the table, you have 1, 2, 3. Values of 1, 2, and 3 are known. Do we have the value of 4? Okay, no. Then we go to fib of 1. Do we have the value of 1? Yes. Put it here. Do we have the value of 2? Yes. Put it here. Do we have the value of 0? Yes. Yes. So simple. This whole thing gets cancelled out. You don't need to use this. You don't need to perform this dividing again. That is the power of storing it, or this is called as memorization for trees or graphs or whatever you call it. This is a top-down approach. So remember, whenever you have a top-down approach, your table filling is going to be bottom-up. You fill from 0 to 5. Now, if you go towards the same thing, if you see the code is a little bit different. This is nothing but approach of tabular approach, where what you do is you store all the values in table. Now you notice how this will work. If you store here in 10, if you take it as 5, it goes from here and then starts returning. It starts filling from back. Basically, it's opposite. If you have a bottom up, this is tabular, so complete table I'll teach you. This is n. So n less than 1 returns it. Otherwise, you put f of 0 as 0, f of 1 as 1. So what does it do? 0 as 0, it should be 1 here. But yeah, so it should be, okay, it should be 0 itself. 0, 1. So as you see, the table is filling bottom up itself. This is not a recursive tree. This is a tabular method, because array method. Okay, and you are this thing to not get you confused. This is array method. Consider this as array. So how is the array getting filled? Bottom up. So there are two ways to do this: memorization and tabular, or array. If you guys don't get confused. So memorization is nothing but store the different space or different table. And tabular is store this array in a different table. That is what these two searches, these two top like best possible of easiest way to understand dynamic programming is. So now, as I told you, I'll be solving a problem called as longest common subsequence, also called as LCS. So what exactly is LCS? As simple as this: you have been given two strings. You have to find the longest common subsequence. Now, what is longest common subsequence is, if you take a variable a in the string x, you have to find a subsequence starting from a, ending till whatever you want, whatever possible, where it's common between both. Now, if I see here, if I start from a, I have nothing. I have to start from here. Okay, after a, what do I have here? I have b. Do I have b here? Yes, I have it. But after b, it's c. Is c here? No, it's not. So your first common subsequence would be AB. Then we'll go to B. Is B starting? Yes, B is starting. C, is C there anywhere after B? Yes, it is there. You can see it. And then next we'll go to B. Is B anywhere after B? Is B anywhere after C? Yes, it is there. We'll go. Then we'll go to D. Is D anywhere after your C which you have found out? No, it's not there. So you stop it. So you keep comparing this one by one and find the longest possible subsequence, longest common subsequence. As simple as this, you can always go forward, never go back. So if you have started with A here and you find your A here, you cannot search anything behind this A. This is over. You have to search only ahead of it. So next is your B. Do you have B? Yes. Do you have C? No. It is present here, but you have to go forward. It's forward. You can't go back. That's your subsequence formula. So that is what your longest common subsequence would be. So here there's another example, and there are solutions for LCS are possible. There are 4 possible ways. One is brute force, normal, and second is recurrence. And I told you another optimization would be of recurrence, which is not exactly fully optimized, but yes, it is optimized, would be memoization, which I just explained what memoization is. It's used in recurrence. And then you use the DP solution for LCS. I've given the time complexity. I want someone after this session to actually write the algorithm for this. Don't look online. Try to find the algorithm for the brute force solution. I think I've given the algorithm for recurrence. Yeah. So for brute force, you guys try to find algorithm for brute force, and there is a small optimization in that. Try to find that as well. You can optimize in some places for some conditions. That will be given in CP, where you can actually use brute force, optimize it, and pass your test case. So you guys try this as your homework. Find the brute force algorithm and try to optimize it a little bit. So what is brute force solution? Take X and Y. For every subsequence in X, check if there's a subsequence in Y. And what is the time complexity of this? If there are 2 power m subsequences of X, that is if you have A, B, A, C, whatever example which I've given, right? So A, B, A, C, A, D, it keeps going on. There, you have to take n search time. Obviously, when you want to search linear time, it is nothing but O(n). Keep scanning from first element of the string to second element. So the time complexity, obviously, when you calculate time complexity, you take the worst case always, because you have no idea what sort of inputs you'll get in CP. You get around like 200, 300 inputs. So consider worst case. Nothing but multiply these two. As simple as that. So the time complexity of brute force would be n into 2 power m. Now let's try the same thing which I said LCS using recurrence. How does recurrence work? If I take example of A as this, the string is B and D, and my B string is A, B, C, D. How do you use recurrence? If you reach end of the string anywhere, if you reach end of the string here, slash 0 is nothing but your end of the string, or here you return 0, because obviously there's nothing found, there's nothing there. And if, what did I say, if both of them match, that is where your subsequence starts. You start it. If both of them match, you return that plus 1 plus of that. Else you return the max of the row. Okay, when I tell table, I'll tell it the max of A plus 1 and the max of B plus 1. And how this works, I'll tell using recurrence how it actually works. Now let's take this example. If I take A of 0, obviously start with 0, I and J. I is nothing but for A and B is nothing but, and J is nothing but for B. So start A of 0 and B of 0. What is your A of 0? B. What is your B of 0? A. Okay. Now what do we do? Now let us see. Is it not equal to 0? Is it equal to the end of the string? No. So we are not returning 0. If both of them are equal? No. What do? We return max of LCS of I plus 1 comma j and I comma j plus 1. So now we'll divide this. I plus 1 comma j is here. I plus 1 of 0, where I is 0. So 0 plus 1 is 1, and you keep j as constant. And divide this again. What is here? I comma j plus 1. So your I remains constant and your B remains, B is j plus 1, 1. So now let's move to the left half, and then we'll come back to the right half. That's how your DNC works. So now let us compare. Let us go here. D and A, are they equal? No, D and A are not equal. A of 1 is D and B of 0 is A. Not equal. So again, we do the same thing. I plus 1 comma j and I comma j plus 1. What is I plus 1 is nothing but A of 2 and B of 0. So here A of 2 is nothing but your end of your string, and B of 0 is nothing but A. So now we have hit end of the string. So what is the value of this this A part? This division is nothing but 0. Now we come back to the right half of this, where you add B value, J value as 1. So here you get A of 1 and B of 1. A of 1 is nothing but B, and your A of 1 is nothing but D, and B of 1 is B. Are they both equal? Check this statement. No, it's not equal. What do? Again, divide it. So divide it again, use I plus 1 comma j and I comma j plus 1. So I plus 1 comma j results you A2 B1. And you know A of 2 is nothing but your end of your string or slash 0. So you put this as 0, don't need to check it. And after this, we'll go to the other half, which is I comma j plus 1. A1 B2. A1 is D, B2 is C. Are they both same? No, divide it. Keep dividing it. I'll just tell you the cost. So if A2 is nothing but end of a string and end of a string means 0, so leave that. And here is where you get your first matching. A of 1 is D, B of D is 3. So both of them are equal. Yes, this becomes 1. And what happens if both of them are equal? You return 1 plus I LCS of I plus 1 and J plus 1. What is I plus 1? A of 2. J plus 1, B of 4. 1 plus slash 0, 1 plus 0. So this is nothing but 1. Now do the same for a right hand side. You'll get the same value and then you backtrack. How do you backtrack? Take any one of your half. If I take my right half, any one, okay. So this, what does it come here? You have your value as 1. And what do you do of this? Return the max, right? This is max. So when you backtrack, you go from bottom to up. So max of these two is what? 1, okay. Max of 1 plus this thing. Max of this is what? 2. And we go towards the left hand side. You have 1 here. Max of this is 1. Max of 0 plus 1, 1. Max of 0 plus 1, 1. So max of 1 comma 2 is 2. Simple. This is your recurrence wave. As I told you, it's exponential time when I explained you Fibonacci. Now, how do you reduce the time complexity of this using memoization? As simple as this. Using memoization, do this. What did I say? Create a table or create any place where you store all your values. So if you see this graph, as you can see, there's something repeated. This is repeated and this is repeated. So this is indirectly increasing our time complexity. Like this whole part should not exist. Why? Because you already have this here. So if you have this here, why are you doing this again? It's a waste of your time and space. So simple as that. Store every single variable. And as I said, if this is a top to down, your table filling starts from bottom to up. So we'll go for 2 comma 0. Where is your 2 comma 0? It's nothing but 0. You just keep comparing everything where your A is 0 comma 2 and you keep doing this. So 2 comma 0 is where your A comma slash n is. So find where your A comma slash n is. It is here. So it's 0. Like that, keep going and you keep finding the weights or the values of this. And after you find the values, you store it. So when you reach here, right, which is D comma C. So when you reach here, D comma C, it is stored. D comma C is already stored. What do? You just go and output it. D and C. This is your D value. This is your C value. It is 1. So you don't need to search. You keep this as 1. So this whole thing gets removed because you don't need it anymore. You already found the value of it. You don't need to split it or divide it again. So that is how you do it using memoization. So why isn't memoization used, or why recurrence we don't use it? Yes, it gives you a lower time complexity, but we can make it even faster. How? Basic DP, which is nothing but tabulation. We store it in the form of tables. So this is how you should do it. This is nothing but like in case of you don't want very low fast time complexity, this technique you use only when your main question given in CP is only based on your recurrence relation. You get it? If your LCS is the main part of your question, which obviously doesn't come, you can use this method because your time complexity is low. Why go faster? Because what if this is only a subpart of your question? What if after using LCS, you have to use something else or perform something else? Obviously, if your LCS itself, the time complexity of this is nothing but M into N, right? Because M searches into N searches. That's it. So what if you want it lower than this? How do you go? Use DP using tabulation. What is the algorithm for DP for tabulation? As you see, both of them are almost same, this thing, but there's not much difference. But here we use in a table and we store it and then we decide it. So this is your basic algorithm. Keep that in your mind. I'll be using this algorithm to explain what it actually does. How do you start with DP? Simple. You take a table, as I told you, tabulation method. Initialize the first row and first column of the matrix where you store the LCS, length of LCS. Obviously, you have to find the length, right, to find the longest common sequence. The highest or the biggest length it is, that's your longest subsequence. As simple as that. So you store the length And first initialize everything as 0, first row and first column. Then you calculate the LCS, keep moving for I comma j, for 1 comma j, 2 comma j, keep doing like this. Store all of them in a table and you point an arrow to the array element that was used in computation. So the computation is mn, which is what I said here. This is the fastest we have. So I'll tell you what this does or what these steps do or why do you use it using this example where I've taken x as ABCB and y as BDCAB. How it works, simple. What is your first step? You have given your ABCB, which is nothing but your first array, first string and your second string. Length of each string is 4 and your length of second string is 5. So what is your array size going to be? 4, 5, as simple as that. Ignore this 0 is nothing but for the storing where you store the zeros, first and first column. So what will your first step be? Initialize your this thing to 0. So all of these become 0. That's your first step. Okay. Now what is your next step? Take your first letter of your both strings. Okay. Now you compare. If A is A equal to B, is it equal? No, it's not equal. So your first condition is wrong. What is your second condition? You find the max of the previous row and the previous column. Okay. So if this is my A, my previous row is this, my previous column is this. So I have to find the max of this. So max of this is nothing but max of 0, 0, which is nothing but your 0. Okay. That is your first table value. Now we'll go towards the next one. After A, B comes A, D and C. You compare A with D and you compare A with C. Now you compare A with D. What is it? Is A and D equal? No. Then again, obviously you take the max of the previous row. This is your row which you're finding, right? This is your cell. So to find the max of this is nothing but the previous row and the previous column. As simple as that. So you find the previous row and previous column, you'll get 0. Again, do the same for C, you'll get 0 again. That's your this thing. Next comes, you search again. After D and C comes A. Are they both equal? Yes, they're equal. What do? C of I minus 1 comma J minus 1, which is nothing but your diagonal element. Because if this is your, this one, right? So this is your cell, minus 1 of this and minus 1 of this is nothing but this. Add 1 to that. You'll get your value as 1. This is your value. And I'll tell you why you're doing this in the end, why you're storing this. I hope you have realized y1, y2, because obviously this is 1 means your longest sequence is 1. Next, we'll move on to A and B. Are they equal? No, they're not equal. Then what do? You take max of previous row, previous column, which is nothing but 1. Yes, because it is going to be 1. Now we'll go towards next one. Obviously, we scan through the entire string. Then we go to the next of the first string, B. Go towards B. So first, what do you get of B comma B? B comma B are same? Yes, they are same. So you just append the diagonal to 1. That's your value. Then we go towards the next 3. BD, are they same? No, they're not same. So what you do is find the max of the previous row, previous column, which is 1. Okay. B and C, are they same? They're not same. Find the max of previous row, previous column, which is nothing but 1. Then you take B and A, are they same? No. Find the max of previous row, previous column, which is 1 again. Then you go towards B comma B. Are they same? Yes, they are same. So what do you do in this case when they're same? Take the diagonal element and add 1. So your diagonal element is this, add 1 to this, so this becomes 2. As simple as that. 2. Now we go on to obviously B has scanned through the entire string. We'll go to the next letter in your string of the first string, which is C. Use C and scan the entire string. Let's go towards C, where you get B and D. Are they equal? No. So what do? Max of previous 1. And then we go towards C comma D. C comma D, are they equal? No. Max of previous elements, this thing 1. And next we go towards C comma C, where yes, they are equal. What do? Add 1 plus diagonal. So it's nothing but 1. Now 1 plus 1, 2. Then you go towards A and B. Your A and B is nothing but max of 1 comma 2, which is 2, and max of 2, and then you have max of 2 comma 2, 2. Then we go towards the last letter of the string, which is nothing but B, and compare this with our second string. B is B equal to B? Yes, it is equal to B. What do? Take diagonal and add it to 1, so it becomes 1. Then you compare with the rest of the stuff, which is why you've taken DCA as simple as it, because your B is common. So just to go faster. So your DCA, take max of this and this, 1. So max of this and this is 1. So max of 2 and 1 you take for C, which is nothing but 2. Max of 2 and 2 for A, 2. Now finally we arrive at the main this thing, which is nothing but b comma b. What is the b comma b? Both are same. So what do? Diagonal plus 1. So 2 plus 1 is 3. Now you finally found the value, the longest common value found, the length of LCS. Now how do you actually find the longest common subsequence from this table? It's as simple as this. For finding LCS, find the diagonal before this, okay, where it's same. The moment it's same, go backtrack. Okay, it's same, backtrack. Keep backtracking until you find your common signal. Everywhere it's common, you keep backtracking. So 3, b comma b, yes, they are same. So it becomes your diagonal. Okay, then you go a comma c. Are they same? Are c and a same? For longest common subsequence, it's simple. From your first string and second string, the element should be same. So what we're doing is comparing the first string and second string x and y and checking where they are same, we go up diagonally. Why do we go up diagonally? I'll be telling you why. So B and B are same, so you take 3, okay, and you move up diagonally. You go here, A and C, are they same? No, then you move left. Obviously, you don't move right because you keep reducing. Then you see here, C and C, are they same? Yes, move up. Okay, compare this. D and B, are they same? No, move left. B and B, are they same? Yes, that's it. That's where it's over, because after B and B, there's nothing constant or nothing same. So your path is nothing but wherever your diagonal, where you move diagonally, that's your LCS, the longest common subsequence. So here, 3, you move diagonally, so it's B comma B. Then where else do you move diagonally for 2? Here. Then it's B, after B comes C. And again, you move diagonally next, when next you move diagonally here, which is nothing at B comma B. So your LCS is nothing but BCB. And this is the reversed order. And then you finally, after obviously when you're backtracking, right? So it's reverse. And finally you straighten it. Here there's a palindrome. That's why it's BCB. You straighten this and then you get your actual normal order of LCS. So this is how LCS works. So I would give you other stuff to try of DP using this only. Logic is same, okay? So there's one called maximum contiguous subarray. So if you guys have time, I will be giving you links if you guys want. If you tell me, just message me in the group if you want link for that. So maximum contiguous subarray, learn that as well for your DP, because it's called as I don't know how to pronounce it, but Cadence algorithm. So that is a very famous DP algorithm. Why is it so famous? This is for strings. Okay. Now, if they tell you to find, this is for largest common, longest common subsequence. Now there's another question like this for strings for array, which is nothing but in an array of n elements, find the largest common, largest continuous sum in the array. So if you have like the array as 1, 3, 4, -2, and 3. Okay, so your let's keep this as 0 only. So what is your largest common subsequence in your array is nothing but 1, 3, and 4. So this obviously again, it you have to keep comparing. Brute force is nothing but what? Take one element, okay, add all of them. Then take the second element, add all of them. Keep adding that, store the sum variable, and when your sum is the highest, put it out. So for this, the time complexity of this is n cube. And obviously you can optimize that as well. So try the optimized brute force as well. If you want, I do have the algorithms for them. I will give that as well. And then finally try to do DP in this as well. The logic is same. This is nothing but longest common subsequence, which I told for strings. And why I didn't use the maximum subarray question is because obviously strings is a little bit harder than your subarray one, because array everyone has worked with. So I've given you an example of how your longest common subsequence works over a string. You guys try out how maximum subarray sum works. So you guys can check that. And this is the end of the session. If anyone has any doubts, you guys can ask.
Bro, in Sublime Text, is there any option for auto spacing?
Auto formatting, yes, there is. I'll give you a video on it. I use that. So
Okay,
I
so
guess,
please share the video.
yeah. So what you do is, okay, I'll share you the video. You bind your Control Shift B, right? That's your shortcut for building. So you
Yeah.
bind your formatting to your building. I'll send that video in the group WhatsApp link of how
Okay.
to do it.
Thank you. Thank you.
Neeraj, you are
Also-
done, right?
Yeah, I just wanted to say one thing. Last time, last contest which you guys gave, right? So if you none of you knew what like penalties